Welcome to the Deep Dive. Today we're digging into a really interesting paper that tackles a pretty fundamental issue for real-time AI. How do you get a vision language model to understand video that just keeps going forever?
Exactly. We're looking at streaming VLM, real-time understanding for infinite video streams. And this is super important for anyone building actual AI assistants, robots, autonomous systems, things where the input doesn't just stop after a minute.
Yeah, the real world isn't neatly clipped videos. So the core problem they address, just to summarize right at the top here for, the key takeaway.
Right. The big issue is that standard VLMs, they just can't handle long videos. They run into this OTT compute cost thing, basically. Memory and latency just explode as the video gets longer.
And the simple fix, like just looking at a sliding window of the video, that breaks the understanding, right? The model gets amnesia.
Totally. Streaming VLM's big idea is this alignment, making sure the way the model trains actually matches how it needs to run during inference, especially with memory limits. They use this clever key-value cache, the KV cache.
Okay, and that cache is smart about what it keeps.
Yeah, it holds on to these attention sinks, like initial prompts, then a good chunk of recent text history, maybe 512 tokens, but only a short window of recent visuals, like 16 seconds. And critically, they use something called contiguous rope E to keep the positional information stable even as old stuff gets dropped.
And it works, performance-wise.
Oh yeah, they're getting stable real-time speeds up to 8 frames per second on an H100 GPU. And on their new long video benchmark, InStreams Evil, it actually beat GPT-4o Mini quite handily, a 66% win rate. Pretty impressive.
Okay, let's unpack that properly then.
Yeah.
Why do these incredibly powerful VLMs that we have, the ones that work great on, say, a YouTube clip, why do they just completely fall apart when you feed them a continuous stream?
Well, it really comes down to the transformer architecture itself, specifically that attention mechanism. With full attention, every new piece of information, every token has to look back at every single previous token.
Right, and if your video is hours long, the number of tokens, T, gets huge.
Exactly. And the computation cost grows quadratically with TOT. That means your memory use balloons, your latency goes through the roof, and eventually, boom.
The dreaded OM, out-of-memory error.
Yep. Figure 1A in the paper shows it perfectly. It's just not a sustainable path if you want something running continuously.
So engineers tried to fix this, right? The obvious first step is the sliding window. Just, forget the old stuff.
Right, but that leads to its own set of problems. If you just chop the video into chunks and process them one after the other without any overlap.
The model forgets what happened in the last chunk.
Precisely. Context gets reset constantly. Imagine trying to follow a sports game commentary if the commentator forgot the score every 30 seconds. It just doesn't work for tasks that need that continuous understanding.
Okay, so then you think, all right, let's overlap the windows, keep some context.
You do that, you maintain coherence, which is good, but now you're recomputing stuff you've already processed in the overlapping section.
So the latency shoots up again.
Way up. Figure 1C shows this, that redundant computation makes it impossible to run in real time. They measured latency hitting 0.4 seconds per token sometimes. That's just too slow.
So this is where streaming VLM comes in with its different approach. You mentioned the streaming-aware KV cache and this idea of asymmetric retention. Break that down for us. What's asymmetric about it?
It's about recognizing that visual information and text information have different values and costs over time in a stream. Think about it. Keeping lots of old video frames is super memory intensive.
Right, high resolution, lots of data per frame.
Exactly. And often the really old visual details aren't that crucial for understanding the immediate next step. But text. Text is cheap to store, and the history, the narrative, the conversation, the score is often vital for long-term understanding.
Okay, so it prioritizes keeping text history over visual history.
That's the core idea. Their cache, as shown in Figure 3, keeps 3 main things. First, these attention sinks, or T-text. These are just a few initial tokens, maybe the system prompt, that are never kicked out. They act like an anchor.
So they stabilize the attention process over the long run?
Correct. They use 512 tokens for this. Second, they keep a longer window of recent text tokens, T-text window, also around 512 tokens. This maintains that conversational flow, the recent narrative.
And then the vision part is where the asymmetry really kicks in.
Yes, the short vision window. They found the sweet spot was keeping only the last 16 seconds of visual tokens. Older visual information is the first to get evicted.
Only 16 seconds. Wow. How does it cope if something visually important happened 20 seconds ago?
Well, the idea is that the model is trained to rely on the text history to bridge those gaps. If something important happened visually, Hopefully the text commentary mentioned it, and that information is still stored in the longer text window.
Ah, okay. So the text becomes a long-term memory for visual events too, in a way.
Pretty much, yeah. It's optimized for use cases like real-time commentary where that synergy exists. This drastically cuts down the memory needed for the cache.
Okay, that handles the memory.
Yeah.
But you mentioned positional information. When you're constantly dropping old tokens and adding new ones, how do you stop the model getting confused about where each piece of information belongs in the sequence? Standard positional embeddings would break, wouldn't they?
They absolutely would. That's positional drift, and it kills performance on long sequences. This is where contiguous rotary positional embeddings is fundamentally important.
Contiguous ROBE, what's different about it?
So with normal ROPE, if you just drop tokens, the remaining position indices become gappy, or they might even shift outside the range the model saw during training. Contiguous ROBE fixes this, as tokens get evicted from the snart of the cache.
You just shift all the remaining indices down.
Exactly, you left shift the indices. So the position numbers stay contiguous, they stay bounded, and critically, they stay within the numerical range the model was trained on. It prevents that drift. Their ablation study in Table 4 shows its starkly native rope falls off a cliff. Contiguous rope keeps it stable.
Okay, brilliant inference mechanism. But you can't just bolt this onto any old VLM and expect it to work. The model has to be trained to understand this whole streaming, cache evicting process. How did they do the training?
Yeah, the alignment between training and inference is key. They used a supervised fine-tuning strategy they call overlapped chunk full attention. Sounds a bit complex, but it's actually quite elegant.
Okay.
They take the long training videos and chop them into chunks, say 24 seconds long. But crucially, these chunks have a big overlap, maybe 12 seconds.
So the second half of one chunk is the first half of the next chunk.
Precisely. And during training, within each 24-second chunk, the model performs full attention. It learns to connect the end of the previous context, which it saw in the overlap, to the new information.
Ah, so that overlapping full attention within chunks essentially mimics the behavior of the attention sinks and the sliding window cache at inference time. It learns to bridge those gaps naturally.
You got it. It simulates having that continuous context during training, even though it's only ever looking at a short chunk with full attention.
And there was that other clever bit about interleaving tokens, teaching the model when to generate text versus just process video.
Right. That's vital for real-time commentary. Instead of feeding all the video tokens first and then getting text out, they interleave them at 1-second intervals.
So for each second, there's either a visual token and a text token if there was commentary, or maybe a visual token and a special silence token.
Exactly that. They used a placeholder token, just seat. This forces the model to learn the rhythm, the cadence, when to speak, when to observe silently. It's synchronizing generation with the visual input second by second.
That makes sense. Now, to train this, you need data that looks like this real-time stream. They built this ImStreams data set from, 4,000 hours of sports?
Yeah, a massive amount. Basketball, soccer, hockey, baseball, American football. They started with automatic speech recognition, ASR on the commentary.
But ASR isn't perfect, right? Especially with background noise. Ads.
Far from it. The raw transcripts were a mess. Ads, irrelevant chatter, sometimes just plain wrong names or actions. So they had to clean it. And get this, they used GPT-5 for the cleaning.
Wait, GPT-5? To basically proofread and edit 4,000 hours worth of sports ASR. That sounds intense.
The intensive, a huge data curation effort. GPT-5 segmented the commentary and then classified each bit, keep, delete, or edit based on quality rules. They ended up keeping less than half, about 46%, and editing nearly 38% of the ASR output.
Wow, that level of cleaning is serious.
It shows how important high-quality, relevant data is for this kind of specific task. And then they did one more fine-tuning step.
The high-quality annealing data.
Yeah, this was like the final polish. They took about 15,000 samples that were specifically focused on real-time, on-field action commentary. At least 80% of the text had to be that. This really honed the model's ability to describe what's happening right now.
Okay, so the architecture is smart, the training is aligned. Does it deliver? What do the results look like in terms of actual real-time performance and quality?
It really seems to. The efficiency numbers are probably the clearest win. Figure 7 in the paper is key here. Streaming VLM just cruises along with latency staying stable and low, well under that 0.1 second per token mark needed for real time, even after processing over 1,000 seconds of video.
While the other methods either crash or get progressively slower.
Exactly. Full attention hits OM, sliding window with overlap just gets slower and slower, hitting that 0.4 seconds per token mark. Streaming VLM stability allows it to hit that 8 FPS on a single H100.
And the quality of the output over those long videos, that 66% win rate against GPT-4o Mini on their benchmark sounds strong.
It is, especially because that InStream's Evil benchmark uses videos averaging over 2 hours long. It shows the asymmetric cache and contiguous ROPE are really working to maintain coherence and quality over extended periods.
What I found really interesting, though, was the generalization. They trained it for commentary, but it actually got better at general vision language tasks.
Yeah, that was a bit surprising, but it makes sense. Table 3 shows it outperformed its base model, Kin 2.5 VL7B Instruct, on standard VQA benchmarks, even though it wasn't explicitly trained for them during the streaming SFT. It saw almost a 6% jump on OVO Bench real-time.
So teaching a model to handle streams makes it better at understanding vision and language overall.
It seems that way. Forcing it to manage context efficiently and continuously might strengthen its core reasoning abilities.
And crucially, did it maintain that performance over the entire length of those long videos? Did it start to fade near the end?
Nope, rock solid. The appendix shows the win rate was consistent across the whole video length from the first 20% to the last 20%. No degradation. It truly seems to support unbounded inference.
So wrapping up this deep dive, it really feels like they've hit on a core principle. This tight alignment between a training strategy that overlapped chunk, short context approach and an inference mechanism built for streaming the things, the asymmetric cache, the contiguous ROPE, that alignment seems to be the key.
Absolutely. It elegantly solves that inherent conflict between needing long-term memory for coherence and needing low latency and bounded memory for efficiency. They found a way to have both, at least for these kinds of streaming tasks.
Which leads us to the final thought for you, the listener. We've seen how this recipe attention syncs, plus asymmetric sliding windows, plus contiguous ROPE works incredibly well for continuous video input. How generalizable is this pattern? Could this idea of aligning training and inference for efficient, stable, long context processing be the blueprint for real-time AI dealing with any kind of continuous sensory stream, maybe audio, maybe sensor data for robotics? Is this the key to more general real-time multimodal intelligence?